11.4 is the big chapter, or big section rather, from chapter 11, and all about colligative properties. So a couple of disclaimers before we get rolling this. It's a big section, right? It's going to be a longer video, so feel free to break it up into smaller chunks. You know, stop halfway, take a break, jump back in. There's 4 colligative properties we're going to talk about, so you can divvy them up by individual property like that. Don't try and take it all at once unless you're really ready to sit in and commit to this section. It's really not math difficult. It's just knowing what equation to use and what everything means within an equation. And on that note, we will have extra problems for practice for those of you that are enrolled in the review session. So if you're not there, I encourage you to sign up for the review as well. All right, but let's get into it. 11.4, colligative properties. Okay. Now, we've talked about phase transitions in solids and liquids and gases with chapter 9, 10, and the first part of 11, but we haven't talked a whole lot about solutions. And the properties of solutions are different, right, than a solute or a solvent on their own. When we have a solution, the properties will change, and we need a way to describe those. Okay? And that comes down to colligative properties. Okay? And what's neat about these colligative properties is a lot of them depend only on the concentration of the solute, not the chemical identity of the solute. Okay? So the concentration is significant, the chemical identity less so, okay? Except for if it's electrolyte or a non-electrolyte, which we'll talk about at the end of 11.4. And listed below here are the 4 colligative properties that we will talk about: vapor pressure lowering, boiling point elevation, freezing point compression, and osmotic pressure. Okay? And you'll see that these two in the middle have very similar calculations. Acidity, that's another one. Density, viscosity, but those 4 that are listed, those are really what we're focused on here in 11.4. Okay? But before we can get into those, we're actually going to get a new concentration unit here in chapter 11, and that's called molality, not to be confused with molarity. And molarity we have from Chem 1550. This is molality, and the only difference there is we switched the R from molarity to an L in molality. Okay? And whereas molarity is represented by capital M, molality is represented by a lowercase m. Okay? It's its own unique unit. We've got molality, little m, molarity, capital M, and also remember from chapter 9, mole fraction, which is represented by X. Okay? So make sure you know all 3 of these concentration terms. We'll use them all in this chapter. Okay? And molality is something that we need to use in chapter 11 because it doesn't vary with temperature. Changing the temperature will change the molarity of a solution, but it does not change the molality. And there's more on that in your textbook if you're interested in why. But right now, this is what the key takeaway is. Molality, represented by lowercase m, is equal to moles of solute divided by kilograms of solvent. Okay, so you'll notice the numerator is actually the same as it is for molarity, but the denominator is not. Okay? Whereas we have liters of solution for molarity, here for molality, it's kilograms of solvent, okay, which is important because some colligative properties use molality. Okay. So here on slide 34, we have a practice question. Okay, this is contained within the notes, or you can pause the video here and try it on your own. What's the molality of a solution with 0.850 grams of ammonia and 125 grams of water? Well, we need to do some conversions to get molality specifically. We need to convert this from grams of ammonia, which is the solute, into moles, convert that 125 grams into kilograms, and then put one over the other. You should end up with 0.399 as your final answer. We can go over this problem in the review session as well. And the way you say the units on that, if we're talking about molality, you would say the solution is 0.399 molal, M-O-L-A-L, a 0.399 molal solution. Yeah, so that's our new concentration unit. Let's actually get into the colligative properties. Yeah. First one that's up is vapor pressure lowering. We've talked about vapor pressure before, right? When we've got a liquid and a gas in equilibrium with one another, okay? Meaning that the rate of vaporization and condensation are occurring at equal rates. Okay? we measure the pressure from the gaseous phase, and that is the vapor pressure. Okay. Now that we can think about for anything, right? Even just a pure liquid. But when we have a solution, right, putting a solute in there always lowers the vapor pressure, okay? Which is, I mean, you can get that right from the name, right? Vapor pressure lowering. And the reason for that is because when we put a solute into our solution, or rather a solute into our solvent to form a solution, that means there are fewer solvent molecules that are present at the surface, okay? Meaning fewer of them are in equilibrium and the gas phase pressure goes down overall, right? So here we see what that looks like visually. Pure water, they're in equilibrium. However much pressure we have is the vapor pressure. But all of a sudden, we put in this purple non-volatile solute, right? Now there's less things that are at the surface, less water molecules or solvent, whatever your general solvent is, in the gas phase, lower vapor pressure overall. And we can actually do some math with this using Raoults' law. And what that tells us is that the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure component, which is this, P naught A, multiplied by its mole fraction. Okay? So the vapor pressure of any component, right, is equal to its mole fraction multiplied by the vapor pressure of the pure solution. Right? So here's Raoults' law. We'll use this to do some math. Right? The partial pressure of whatever we're looking at, just calling it A in general, is equal to the mole fraction multiplied the vapor pressure of the pure solution. Here's another one for practice, right? There's going to be a practice problem for each one of these colligative properties. If you want to be confident in chapter 11, I mean, you're going to have these on sapling, you'll have these in the review session. Right? They're definitely going to be on the test, so make sure you know how to do all of the types of calculations you see in 11.4. This one is vapor pressure. Okay? If we have a solution that contains 5 grams of urea, which is a non-volatile solute, we'll always be dealing with non-volatile solutes for vapor pressure, and 0.1 kilograms of water, right? We're given a vapor pressure at 25 degrees Celsius equal to 23.7 torr, right? Unit of pressure. We can keep within that unit because we're not asked to do anything else. Now, what's the vapor pressure of the solution? So we're given lots of information, right? Vapor pressure of the pure substance, right, is 23.7 torr. We know our final answer should be lower, right? Because it's vapor pressure lowering. So what do? I have to calculate the mole fraction of my solution, right? Because I'm asked about the vapor pressure of the solution. So you figure out how many moles of urea I have, how many moles of water, okay. Then solve for the mole fraction of water and multiply it by the pure vapor pressure. Okay. If you do all that, you should get a final answer of 23.4 torr. Any questions on that? Right, you can post on Blackboard, send me an email, or again, we can look at that in the review session. Okay, more on these to come, or more practice problems to come, rather. So vapor pressure lowering, colligative property number 1. Okay. Number 2 is boiling point elevation. Just like vapor pressure gets lowered, boiling point goes up. And the two ideas are kind of related to one another, right? We've established before in chapter 10 that the boiling point of a liquid is a temperature where the vapor pressure is equal to the atmospheric pressure. Okay, that allows these particles to escape to the gas phase when it's boiling. Okay? So we know when we make a solution, vapor pressure always gets lowered. That means if the vapor pressure is lower, the boiling point increases because it's taking more energy for that vapor pressure to be equal to the atmospheric pressure. Okay, so boiling points always go up for a solution relative to the pure substance. And we call boiling point elevation delta T sub B. Okay, so delta, change in temperature, B for boiling. And the boiling point elevation is equal to the boiling point elevation constant, okay, which is something that's unique to each solution. It would be provided to you, multiplied by the molality. Okay. So looking at this equation, this is the next equation we have. There's 3 total so far from this chapter. The molality equation, vapor pressure lowering with Raoults law, and here boiling point elevation. Okay, so make sure you know how to use all these different types of formulas. Change in boiling point is equal to boiling point elevation constant multiplied by the molal concentration of the solute. Okay. And if you had multiple solutes, it would be the concentration of all the solutes together. We'll only ever be dealing with one solute at a time. Okay. And again, this boiling point elevation constant will be provided to you because it depends on the identity of the solvent. The only exception would be if I gave you this and this, right, delta TB and molality, and asked you to solve for the boiling point elevation constant. So what's the general strategy here? Well, first we need to calculate the molality of the solution. And then we use that equation to solve for delta TB, which is the change in the boiling point. But keep in mind, right, that the change in the boiling point is exactly that, the change. It is not equal to the new boiling point. Okay, so I'm going to jump back a slide here. We solve for the change in the boiling point to get your final answer for what the new boiling point is, keeping in mind that it always goes up. You have to add that to the original boiling point, which is step 2 there, the new boiling point. Add the change to the boiling point of the pure solution to get the new boiling point. That is the most common mistake I see in chapter 11, forgetting to do that. So don't fall for that. All right, so here's a practice for boiling point elevation. Okay, it asks us what's the boiling point of a solution of 1 gram of glycerin and 47.8 grams of water. We're given the boiling point elevation constant. Okay, so we first have to solve for the molality. That's step 1. Okay, take your 1 gram of glycerin, use the molar mass of glycerin to solve for moles. Okay. Take your 47.8 grams of water, that's your solvent, convert it to kilograms. Okay. Then it's moles of solute over kilograms of solvent to solve for molality. Take your answer for molality, multiply it by the boiling point elevation constant. You get delta TB, boiling point elevation change. Right? So now you add that back to the original boiling point of water, which is not given to you because it's assumed you know it. Right? That's what the whole Celsius scale is based on. 100 degrees Celsius is the boiling point of water. You should have got a final answer of delta TB of 0.12 degrees Celsius. So your final answer here for this problem is 100.12 degrees Celsius. Again, practice, practice, practice. Okay. So why is boiling point elevation helpful? Well, we could actually use different boiling points to our advantage and separate things by distillation. Okay. Depending on how many chemistry classes you take, you might actually do distillation in the lab, okay? But it's used plenty in industry, right? It's used to separate out oil. It's used in the alcohol industry, right? You've probably heard of a distillery. Okay. And using differences in boiling points to separate things out is a big part of analytical chemistry. So boiling point elevation, that was colligative property number 2. Number 3 is freezing point depression. Okay, we're halfway through our colligative property. This might be a good place to take a break, take a breather, and then jump back in. Yep. So freezing point depression. If we have a solution, just like boiling points go up, freezing points go down. Solutions freeze at lower temperatures than the pure liquid does. And that's something we know, right? Living in the southern tier, we use that to our advantage every year when we salt sidewalks. Okay, lower the freezing point, make it harder for that ice to form, and then right, you don't have as much ice on your sidewalk. Maybe you've also seen a de-icer used at the airport. And look at how similar that equation looks. Okay, delta TF now for freezing is equal to KF, freezing point depression constant, multiplied by the molality. Again, exact same approach. Just remember that boiling points go up, right? Freezing point depression doesn't mean that the freezing point's sad, right? It means that it goes down. Freezing points go down, boiling points go up, freezing points go down. So you solve for delta TF and then subtract it from the original freezing point. Keep in mind also, KF and KB are not equal to one another. They depend on the solvent, but water, for example, will have a different value for KF and KB. And just like KB, KF will be provided to you unless you're asked to solve for it specifically. And delta TF equals freezing point depression constant multiplied by molality. Okay. Same exact strategy for solving for this problem. Okay. So we're not going to look at a practice problem right here. We'll have one in the review session because it's literally the exact same as doing boiling point. That's the good news. Okay. Take an aside here and think about phase diagrams of aqueous solutions. Okay? Because when we were looking at phase diagrams in 11.2 and 11.3, right, that was just for solids, liquids, and gases. We didn't talk about solutions at all. Okay? But we can introduce those as well because they're a nice way to show exactly what's going on. The fact that boiling points go up, freezing points go down. Okay? Now the solids and gas phases don't change. They're not subject to colligative properties. We're just talking about liquid solvents here. So the curves still look the same. We just have different values. Okay? So here's what that looks like. Okay? Still the same general phase diagram, solid, liquid, gas, right? But now we can actually see change in freezing point, changing boiling point right there on a phase diagram. And look, there's vapor pressure lowering as well. Okay, so just be aware of what's going on. If you see two different lines here, right, between solid and liquid and gas, you know that that's an aqueous solution in between there. So our last colligative property deals with osmosis. Okay. Maybe you've heard of osmosis, maybe you haven't. Okay. Relates to biology pretty strongly as well. Okay. Now, osmosis occurs when we have what's known as a semi-permeable membrane. Right? So it's a membrane that allows some, but not all things to pass through. Okay? They exist in industry, they exist in nature, you can find them all over the place. But concentration of the solute and the solvent on opposite sides of that semi-permeable membrane can affect how things move through the membrane itself. And that's what osmosis is, the diffusion-driven transfer of solvent molecules through a semi-permeable membrane. So the solvent now is moving through the membrane, not the solute. This is what that looks like. Okay, pure solvent on one side, solution on the other. Right? The solvent particles move through, okay, not the solute. But what we're interested in doing with our colligative properties is measuring how much of the solvent moves through and something that's known as osmotic pressure. Notice the difference in the water levels here. They started the same, but when we establish equilibrium through that membrane, now they're different water levels here. So what is osmotic pressure? Okay, it deals with that accumulation of volume on whatever side has the solute. Okay, because if we have pure solvent on one side and a solution on the other, the solute is always moving into the solution. So that's the side that's going to go up. Okay. So the volume increases on the side that has the solute from accumulating solvent, okay, which having more volume on one side causes pressure pushing back the other way. Okay. And we can measure that pressure when equilibrium is established. It's called osmotic pressure, and this is how we calculate it. Okay. Pi equals capital M RT. Okay. So pi represents the osmotic pressure here. That's what we're solving for in most cases. Okay. M is the concentration, but notice now for this colligative property, we're back to molarity. And that's the trickiest part of chapter 11 and one of the trickiest parts. If you're doing vapor pressure lowering, you're dealing with mole fraction, X. If you're doing boiling point elevation or freezing point depression, you're dealing with molality, okay, lowercase m. And here for osmotic pressure, we're dealing with capital M, molarity. Okay. R is our gas constant that we've used before, and then T is our Kelvin temperature. Putting all of those into this calculation right here allows us to calculate the osmotic pressure, okay, which is pushing down one way, or if we're using it in a synthetic application, the external pressure necessary to push a solvent back into a pure solution, right? If we exceed the osmotic pressure, we can force the solvent molecules back out. And here's what this calculation might look like, okay? If you're trying to do osmotic pressure. What is the osmotic pressure? Okay, so pi, if pi equals MRT, of a solution with a volume of 0.75 liters that contains 5 grams of methanol in water at 37 degrees Celsius. Again, pi equals MRT. Okay, we're solving for pi, the osmotic pressure. So M is molarity. That's what we're going to need to solve for first. Use 5 grams of methanol. First convert grams to moles of methanol. Then take our moles of methanol divided by 0.75 liters. Yep. That gives you your molarity. Your molarity multiplied by your gas constant, right? R 0.08206 liter atmosphere times mole Kelvin. Liters times atmosphere over moles times Kelvin. Not sure if I said that correctly, right? The same gas constant we used in chapter 9. And the temperature in Kelvin, right? So remember, we're not using that 37C. We add 273. And so we're using 310 Kelvin here. Multiply those three together, right? And you should get a final osmotic pressure of 5.3 atmospheres in this case. If you're checking your units, the final unit is atmosphere. Yep. And osmotic pressure is really useful, especially in less developed countries, because this is how drinking water is made from seawater. If you have an area that doesn't have access to fresh water, right, you can calculate the osmotic pressure, right, use an apparatus to exceed that pressure and force solvent through a semi-permeable membrane. You can get clean water. So that's our last colligative property. Again, another possible break here. We got half dozen slides or so to go. And that deals with colligative properties of electrolytes. Because notice nowhere here did we really use the chemical identity unless we had to calculate the molarity, molality, or mole fraction. Okay. But we can have chemical properties or colligative properties be the same if things are non-electrolytes. But what about electrolytes? Okay. Now, our colligative property still does only depend on the amount of the solute that's in solution, right? Depends only on the number, not the kind. But if the thing that's dissolving as the solute is an electrolyte, it can change the colligative properties. So let's think about something like sodium chloride versus glucose. Okay, they both dissolve, yes. But sodium chloride dissociates, whereas glucose does not. Okay, this is an electrolyte, this is a non-electrolyte. Right. So now, every time I take a single particle of NaCl and put it in solution, it breaks up into 2 solute particles, whereas there's just 1 glucose when it dissolves. And that's important for something that's known as the Van Hoff factor. Okay? The Van Hoff factor, which is represented by a lowercase I, is the ratio of solute particles in solution to the number of formula units dissolved. Okay? So for NaCl, for example, the Van Hoff factor is approximately 2, okay? Because for every mole of formula unit of NaCl, we get 2 moles of particles in solution, the Na plus and the Cl minus. Okay, for glucose, it would have an approximate Van Hoff factor of 1. Okay? Now, for the test in this course, if you have an electrolyte, you can assume it fully dissociates and use an approximate whole number Van Hoff factor. And you get that from the chemical formula. Okay? If it's a non-electrolyte, it's always 1. NaCl would be 2. Okay? Calcium chloride, for example, CaCl2 would be approximately 3. Okay? Ca2 plus and 2Cl minus when it dissociates. Sodium phosphate would have a Van Hoff factor of 4 because you get 3 Na plus and then your phosphate PO43 minus. Okay. So on your homework, you'll be given the exact value of the Van Hoff factor. If you have an electrolyte on a test or quiz, you calculate the approximate Van Hoff factor using the chemical formula if it's an electrolyte. If it's not, you don't have to worry about it. But with that in mind, right, it does require new formulas if we have electrolytes. Okay? All of our previous formulas for those 4 colligative properties, if we're dealing with an electrolyte, introduces that term I, the Van Hoff factor, okay? Right there in the beginning of the calculation. If it's a non-electrolyte, no big deal, because the Van Hoff factor is 1, so it just drops out of the equation. Okay, so that's when we have a non-electrolyte. Or if you see a problem, state that you have an ideal solution. that means you don't have to worry about the Van Hoff factor, okay? But if you have an electrolyte, you do. So that gives you a new scheme for solving problems, right? You have to calculate moles of ions in the Van Hoff factor. That will get multiplied by your molality and, in this example, freezing point. Okay. So that is the last consideration from 11.4. Again, this is a really big section. Break it up into manageable chunks. But the big takeaway, what you need to know, right, is really all summarized right here on slide 59. Know what these 4 equations represent, know how to do math with them, and you'll be good with the bulk of the material from chapter 11.